Okay, so this is where we stopped last time. We went through this inclusion exclusion principle. If you want the union of two finite sets, use someone again. It's hard about switching off your microphones. It's not rocket science, man. Okay, so let's continue now. It says if A1 and A2 are two sets, then the number of elements in the union of A1 and A2 will be the number of elements in A1 plus the number of elements in A2 minus the number of elements in the intersection of A1 and A2. I think we showed why this works. So today we'll just make use of this formula. So here we go. Let's apply it to an example. So here's a question which is asking how many bit strings of length 8 either start with a 1 or end with 2 zeros, right? So let's see if we can illustrate this. Huh? So we have two sets of bit strings. So one set will be the set of bit strings of length 8 which start with a 1. So these ones are the ones that start with a 1 and then followed by 8 other bit strings. Then we also have another set of bit strings which end with 2 zeros, right? So we can call this set A and we can call this set B. So we want to find the total number of bit strings that either start with a 1 or end with 2 zeros. So to get that, we need to find the number of elements in the union of A and B. I believe you are familiar with this notation from SMA 101. So is this notation familiar?
Yes.
Yes. So this is what we need. So we can apply the pigeonhole principle immediately and we'll see that this should be given by the number of elements in A plus the number of elements in B minus the number of elements in the intersection of A and B, right? So that's applying the inclusion-exclusion principle. So now the only thing we need to do is to figure out how many elements are in this set A, how many are in the set B, and how many are in the intersection. Once we figure that out, we just plug them into this formula and we have the answer. Okay. So we'll go to the solution now. So the first task will be to construct a bit string of length 8 that begins with a 1. So if you have the bit string of length 8, it begins with a 1, which means the first slot can only be picked in one way. There's only one possibility. So you're left with 7 other slots for the other end. And for these remaining 7 slots, you can pick anything you want, either 1 or a 0. It doesn't matter. You can put either 1 or a 0. So you have 2 ways to fill in each of the remaining slots, right? So if you use a product rule, it means the number of bit strings of length 8 that begin with a 1 will be If you multiply all these, you will get 2 raised to 7, right? So that takes care of the bit strings of length 1. So this can be done in 2 raised to 7, which is 128 ways. Now the second task will be to construct if you have a bit strings that end with 2 zeros, then the last 2 bit strings will have 0 here and 0 here. So you are left with how many? 6, which can be filled in, right? These are 5. So you're left with the 6 other bit strings, which can be filled in two ways. Since these ones can only take 0, it means you can fill this in only one way, and that means the same for the first, the last one here. So these last 2 can each be filled in one way. If you apply the product rule and multiply this, you will see that there will be a total of 2 raised to 6 ways of constructing a bit string of length 8 that ends with 2 zeros, right? So we figure that should be 64 ways to construct a bit string of length 8 ending with 2 zeros. So now the next task is to find the number of elements in the intersection of the 2, and that will be bit strings that start with a 1 and end with 2 zeros. So that one now will be again similar, but we have these restrictions. The first one starts with a 1 and ends with 2 zeros. So if it ends with 2 zeros, it means the last 2 also have, there's only one way of filling each of the last 2 slots. So we are left with 5 slots in between. So we have 5 slots, and each of them can be filled in 2 ways, right? Again, we apply the product rule. Then the number of bit strings that start with a 1 and end with the 0 will be 2 raised to 5. And that is 32 ways. So now we can apply the inclusion-exclusion principle. And we'll have the total number required will be 128 plus 64 minus 32. And that should give us 160. So the answer is 160. Are we together?
Pardon, sir.
Yeah.
Okay. So there are no questions on this. So the next thing we look at is the pigeonhole principle.
Why minus 32?
Huh? Is there a question? No. So the next thing we look at is
He's asking, sir, why have you subtracted that 2?
okay. Now 2 raised to 5 is equal to 32, right?
Yeah.
And then, is your question answered now? Were you there from the beginning of the class?
32 are ways in the intersection.
Yes, that's correct. So we drew some diagrams at the beginning. We said this first set, I called it A, would be the number of ways of constructing a bit string of length 8, which starts with 1, right? And we saw that that is 2 raised to 7. So the number of elements in A is 128. The same way, this second set, we call it B. And we've seen that the number of elements in B is 64, right? Then we're applying the inclusion-exclusion principle, which says that if you want to find the number of elements in the union, so you're looking for all the bit strings, which either start with a 1 or end with 2 zeros. So it will be the number of elements in A plus the number of elements in B minus the number of elements in the intersection of A and B. So that should answer your question now. The number of elements in the intersection of A and B. So it means you have a bit string which satisfies, that is a bit which starts with a 1 and 2 zeros. Is it not? Okay, so we'll remove the drawings now. So the next thing we look at is the pigeonhole principle. So the pigeonhole principle says the following: if you have k plus 1 or more objects and you place them into k boxes, then there is at least one box containing 2 or more of the objects. Let's test this with a simple example. So suppose I have 3 objects. So k plus 1 is, or rather k is equal to 2. I have 2 boxes and 3 objects. So this will be my boxes. I have 2 boxes. So the claim here is that if I'm going to put all these 3 objects into my 2 boxes, one of the boxes will have 2 or more objects. So how can I can try as much as possible to avoid putting 2 in one box. So I take my first object, I put it here. I put the second object here. But then I have no other box, right? These are the only boxes I have to place my objects in. So the third one must fit into either the first or the second. So one of them must have 2 or more objects. So the other way you can do it so that a box has more than 2 objects is if all the 3 are put in one box. So this way, so you can have at least 2, but you can also have more than 2, depending on how you choose to put them in the box. So that's what the theorem says. If you have k boxes and k plus 1 or more objects to place into the k boxes, then there's at least one box containing 2 or more of these objects. So here is a proof. The proof says the following: suppose that none of the k boxes contains more than one object, then the total number of objects would be at most k, right? So that means that contradicts the fact that we have k plus 1 objects. The proof here is by contradiction, and therefore one of the boxes must contain 2 or more. If we assume that none of the boxes contain 2 or more, then we end up with fewer objects than the ones we have, which is k plus 1. So one of the objects must contain at least 2 or more. So that's the proof. So let's see if we can do an example on this. So among a group of 367 people, there must be at least 2 who share a birthday. right? You can see this. So what are the pigeonholes? The important thing is to be able to figure out what the pigeonholes are and what the boxes, what the objects are. So if I have, so my pigeonholes should be what? The number of days in a year. So we'll keep going like that until we get to the last one, which is 366. So each of these is a possible birthday, but I have 367 objects. So I can place, if I want to spread them out in a fashion that there are no two in a box, I keep doing this until I reach the 366th person. So this covers all the birthdays. This is one possible way to stretch them out. But then you still have one more person. So one more person must fit into one of these boxes as well. It can be any of the other boxes. I've just chosen two, but one of this 367th person must fit into one of the 300. There are nowhere else to fit. So there must be at least two people which birthday. So here is a example. Is in any group of 27 English words, there must be at least two words that begin with the same letter. Since they are, this is because you have exactly 26 letters in the English alphabet. Again, the idea here is to figure out what are the boxes or pigeonholes and what are the objects. So the pigeonholes in this case will be the alphabet. So if you count you'll have 26 letters in total in the alphabets that we use in general. So if you have 27 English words, you can pick the first letter of each word and try to put them into these pigeonholes. So if you pick the first letter, the first 26 words will take up all these 26 letters. So the remaining word, or the first letter of the remaining word must fit into one of these, right? So it means there must be at least two words that begin with the same letter if you have a set of 27 words. Is there any question on this? Hakuna swali?
Is there a way that we can work so that the remaining can fit in a given pigeon?
Just repeat your question.
Is there a calculation that can be done? For example, for these English words, the remaining ones should fit in a given pigeon.
That's what I have done.
Okay, then.
How many students must be in a class to guarantee that at least 2 students receive the same score in the final exam? If the exam is graded from 0 to 100%. So we have a total of 101 possible scores, and we want to find the smallest number of students that can be in this class to guarantee that at least 2 students receive the same score on the final exam. So we consider these 101 possible scores as the pigeon points. So for us to guarantee that
Excuse me, sir, we can't hear you.
Oh, so here is a, so how many students must be in a class to guarantee that at least 2 students receive the same score in the final exam if the exam is graded from 0 to 100 points? So there are 101 possible scores here. And if we want to, we take this 101 scores as the pigeonholes, right? So we have 1 all the way up to the last one, which is 101. So we want to guarantee that at least 2 students will have the same score. So if we start placing each student, suppose each student gets a different score, we can stretch it out, put the first student here, the second student in the second slot, and so on up to the last student, which will be the 101st student. So if you have 101 students, it is possible that each of them can get a different score. So if you want them to have a 2 with at least the same score, then you need 1 more student to guarantee. So you'll need 102 students. You need 1 more student to share a score with the others. So the minimum number you need is 102. So the math is 102 that students will have the same score.
What if it remain 100?
So the next one we look at is if you have any questions on the previous one, you can ask before I move.
I have a question.
Oh, okay. You'll ask in a minute. Let me just. Okay, you can ask the question now.
What if it remain 100? The score
Pardon?
remain 100. What if the score remain 100?
There are 101 scores. If you count 0, 0 is a possible score. Is it making sense?
Okay.
Yes.
If you count from 0 to 100, those are 101 possible scores.
It's 100.
Excuse me, sir. Is 103 okay also? Or just 1 or 2?
Only 1 student sharing a marks.
It's at least 102.
Okay, yeah.
Any number higher than 102 will work also, but at least 102 will guarantee. So here is another theorem. This one now is what we call the generalized pigeonhole principle. So if n objects are placed into k boxes, then there is at least 1 box containing a minimum of this number of objects. Now this function is called the ceiling function. When you see this around an integer, so for instance, if I want to find the ceiling of 4.3, then this simply means I pick the smallest integer that is bigger than, the smallest integer that is bigger than 4.3. So that would be 5. The ceiling of 4.3 is just the next integer bigger than 4. The smallest integer that is bigger than 4.3. So that's what the ceiling means. It's called the ceiling function. The ceiling function, like that. So I hope that makes sense. So fine, let's look at the proof. So again, we'll prove this by contradiction. We are claiming that there must be one box that contains at least this. So we can prove this by contradiction. So we assume that it's not true, that none of the boxes contain this number of elements. So that means there's no more than this number of objects. So the smallest you can have should be less than this, right? So suppose the smallest number of objects you can have in any box is less than this, and that is would be n over k minus 1. Then the total number of objects cannot exceed n, right? Because then you have k boxes, and the maximum number you have in each box is this. So you multiply that by k. But then that will be strictly less than this. So we are using the following. Let me just state something here. If you have n over k, is n over k, the ceiling of that, it will always be less than just working out n over k plus 1. This is true. So this is always true. So if we replace this n of k by something which is larger than this, right? Then we end up with this less than or equal sign here. It becomes an inequality. But now if you work this out, if you compute all this, you will get n. So you end up with a contradiction that the total number of objects is less than n. But that is not true because the number of objects was exactly n. So this contradicts our initial assumption that number of objects was n, and therefore we must conclude that there must be at least one box with the ceiling of n over k objects in it. Okay, so so this is just explaining the ceiling function. If you put this function to x, it means you pick the smallest integer that is larger than x. And here is an example. We did some of these. I think that should be clear by now. So here is an example where you can apply the generalized pigeonhole principle. It says, what is the minimum number of students required in a discrete maths class to be sure that at least 6 will receive the same grade if there are 5 possible grades? So go back to the theorem. You need to figure out what are the objects and what are the boxes. So we have 5 boxes, and we need the number of objects n, which we don't know what it is. So we make that substitution n over 5. The ceiling of this should be equal to 6. We want to have at least 6 students receiving the same grade, right? So this is what we want to achieve. So so the smallest integer that satisfies this would be n is equal to 5 times 5 plus 1, which is 26, right? Because 25 over 5 is 5, it means you can't have 6, right? So the next integer that will make sure you have 6 should be 25 plus 1, right? which is 6. So the smallest number that you need to guarantee that at least 6 students will receive the same grade is 26. Is that okay?
Yes. Yeah. It's okay.
Okay, we'll move on to the next. So this one is a little more interesting. It says during a month with 30 days,
Yes, sir. I have a
baseball
question.
team plays at least 1 game a day,
Hello.
but no more than 45 games. So they must play at least one.
Excuse, sir.
When they don't play, but they cannot play more than 45 games in these 30 days. So the question asks us to show that there must be a period of some number of consecutive days during which the team played exactly 14 games. Okay, so basically what we are supposed to do is to find, there'll be 30 days. So we need to find a sequence of days. So say maybe if maybe if they started from day 3 to day 4 and so on, a sequence of days and so on. We don't know how long this will be for now, but it should be a series of consecutive days during which they played 14 games. So we have to find a smart way to apply the pigeonhole principle. So you need to pay attention. This is it's not a direct application. You have to sort of cook prepare some recipe first before you. So this is the number of games on or before the J. So for instance, A1 games played 1, and then A2 will be the total number of games played on day 2 and also on day 1, and A3 will be the total number of games played on day 3 and day 2 and day 1, like that. That's what it means. So it's the number of games played on or before the Jth day of the month. So what does that mean? So this list of numbers is an increasing sequence of distinct positive integers. Why is it distinct? Because they must play at least 1 game a day. So if they played 2 games in day 1, the next day they must play another game. So this must increase. 2 must increase. It will be 2 plus at least 1 game they play on day 2. So a minimum of 3 for the next day. It can't be 2. It must be more than 2. So this sequence will be increasing. All the integers will be distinct. There will be no 2 values here that are equal. They're all different. And we know that the number of games played cannot exceed 45, at most 45 games. So a total number here cannot exceed 45. So A30 has a maximum of 45. And since they must play 1 game a day, the smallest value you can have for any of these numbers in here is 1. So now we can also create another set of numbers by adding 14. We'll see why we are adding 14 in a minute. If you add 14, then you get a new set of numbers, which is also different from all this first set, and none of the two, no 2 of these new set of numbers will be equal. That follows from the fact that none of these were equal. So none of these, no pair of this second set of numbers will be equal. And since we are adding 14, this new set of numbers will be numbers between 15 and 59. So if you consider both sets of numbers, if you pull this set and this other set of numbers, you have a total of 60 numbers, and none of those numbers exceed 59, right? So we can combine these two ideas. We have a set of 60 numbers, and none of those 60 numbers exceed 59. The most they can be is 59. So what does that mean? It means you have 59 pigeonholes. So you have 59 pigeonholes, and you have 60 numbers to put in this 59 pigeonholes. This goes all the way up to 59. So if I was to put all these 60 numbers into the pigeonholes, I will get to some point here in my pigeonhole, and then the remaining number will have to be shared somewhere, right? Now, if any two numbers are equal, one of them must be from here, and the other one must be from here, because there's no pair of numbers in this set, first set, that are equal, and there is no pair of numbers here that are equal. So if there are any two that are equal, one of them must be from this set, and the other one must be from this set. Does that make sense? So we have seen why two of them must be equal, at least two of them must be equal. So for them to be equal, we have claimed that we have one number must be from this first set, so we call it AI. And then the second number must be from this set, so it must be some AJ plus 14. So it means between
Yes.
this means that exactly 14 games were played from day J plus 1 to day I, right?
Yes.
Which answers the question. Remember how we describe these numbers? AJ is the number of days of games played on or before the Jth day. So if I J plus 14, we have 14 from the J plus 1 up to I, there's an extra 14 days. 14 there's a sequence of 14 games were played. So we don't know what J is or what I is, but we know that this must happen because of a pigeonhole principle. So are there any questions on this? Any questions? Hakuna swali? So we do one more application of a pigeonhole principle. It says that show that among any n plus 1 positive integers not exceeding 2n, there must be an integer that divides one of the other integers. So what is this saying exactly? If we have, let's pick an example like if n is 5, so 2n will be 10. So if you have n is 5, what will 2n be equal to? 10. So we need n plus 1. So we've taken n is 5. So n plus 1 will be 6. So let's see if we find 6 positive integers not exceeding 10. We need to show that there must be one of them that divides another one in the list. So can you give me a list of over 6 integers not exceeding 10 positive integers? So let's start with 2. Can you give me one more?
3.
3, 4, 5.
4.
You're just choosing the consecutive ones. Okay. This one already has worked. 2.
7.
Let's try to make it not work. So we have 2,
5.
3. Then we pick 5. Then you pick 7.
7.
And
9.
now you must pick one more, because none of these divide each other. We need
8.
2 more.
11.
Let's say, so I can pick 8 and 9. So already I have 2 divides 8 and also 3 divides 9. So at least there must be an integer which divides the others. So that's what the theorem is saying. This is just an example. So this kind of thing cannot be a proof. So if you ask to prove this, please do not give an example like this. I'm just using this example so that you understand what the question is asking. So now we need to go to the proof and see how we can apply the pigeonhole principle to solve this. Irene, please put off your microphone. So let's read the question again. It says, among any n plus 1 integers, positive integers, which don't exceed 2n, there must be an integer among the list that divides another integer. Okay, so so we can pick each of the n plus 1 integers and write them as a power of 2 times an odd integer. This is always possible. For instance, if I have 3, then I can write it as 2 raised to 0 multiplied by 3. This is always possible. If I have what? If I have 10, I can simply write it as 2 times 5, right? So we can always write a positive integer as some power of 2 multiplied by an odd integer. This is always possible, right? You can start. Right, like that. So kj is equal to 2 raised to kj multiplied by qj, and we have n plus 1 of these integers, where kj is some negative integer and qj is odd. So this is what we have said. We get our list of n plus 1 integers and write each of them as a power of 2 multiplied by an odd integer. Okay. So here we have a total of n plus 1 odd numbers, because we have n plus 1 integers here. Each of them will correspond to some odd positive integer. So we end up with a list of n plus 1 odd positive integers, which are all less than 2n. So let's see how this works. Now, if you have a list of integers that are less than 2n, then you can have the total number of distinct odd positive integers you can have is n, right? So if you have a list of 2n integers, so this is 1, 2, keeps going on up to 2n. The number of odd integers can only be half of this, right? Number of odd integers in this list. So we have the number of distinct odd integers here can only be n. So we have a total of n boxes, right? but we have n plus 1 objects to fit into those boxes. So I can put Q1 here, I can put Q2 here, and I can go all the way up to Qn. But then I have to repeat again. One of these will have to be repeated. It will have to fit into one of these already filled boxes. So it means there must be a pair in here that are equal. At least a pair that are equal. You can see that? Is that clear? Hey, you have gone quiet.
Not understanding.
So, but you have understood the fact that if you pick an integer, you can write it as a power of 2 multiplied by an odd integer, right?
Yeah.
Yeah.
Okay. So now we have a list of n plus 1 integers. Each of them will be written in this form, right? So for instance, a1 will be written as 2 raised to, we'll call it k1 multiplied by q1, right? This will continue like this until we reach the last one, so that a n plus 1 will also be written as 2 raised to some power, which we, so subscript n plus 1 down here, multiplied by some odd number, which we call qn, q subscript n plus 1. So there are n plus 1 of these numbers. There are n plus 1 of them. Now these n plus 1 numbers are all odd, right? And all of them are less than 2n. You can see that? So for instance, if you pick n is equal to 5, then 2n will be equal to 10, right? So if I have a list of 6, that is n plus 1, n is equal to 5. So if I have a list of n plus 1 numbers, odd numbers, then I have only 5 numbers to choose from. My 5 numbers would be 1, 3, 5, 7, and 9. For me to have a list of 6 of odd numbers less than 10, then I have to repeat one of these, right? So maybe I can repeat 3, then I have no other odd number to pick from. So I have to repeat one of them for me to have a list of 6. Is that making sense?
Yeah.
Yeah.
Oh no.
Good. So that says we have at least one here that are. So let's continue.
Yeah.
So suppose we pick this pair to be Qi and Qj, and let's assume that they're all equal to some common odd number we call Q. Then if that happens, it means Ai will be 2 raised to Ki multiplied by Q, and also Aj will be the same because Qi and Qj are equal, and we've called the common equal number Q. And once you write them like that, then it's easy to see that if Ki is smaller than Kj, then Ai will divide Aj. You can see that? And also if Ki is greater than Kj, then Aj will divide Ai. So we have confirmed that there's at least one number which divides a second number. So if you pick a list of n plus 1 numbers from a set of numbers that does not exceed 2n, then there must be at least one integer that divides another integer in that set. Is that making sense? So that's the end of the proof. Hakuna swali? So I think we can stop there for today. Unless someone has a question, I think that's a good place to stop. Then next week we can, from next week we can do 2 hours.